Good evening, everyone. I welcome you to the webinar on designing right-sized HVAC with load calculations today. I am Yashima Jain, and I'll be moderating today's session. Next slide, please. Now, first, I would like to acknowledge the support of the Department of Science and Technology and the Ministry of New and Renewable Energy. I would also like to acknowledge the support of various sponsors and affiliates of Solar Decathlon India. Next slide, please. Now we are past the halfway mark of the Learning Online program for Solar Decathlon India. And here are the top 5 teams who are ahead on the self-learning modules. Now you guys are taking the best advantage of the self-learning modules for your Solar Decathlon India entry, and we congratulate you. Next, let's go over a few announcements for today. Next slide, please. Now we have completed our review for your deliverable 1, and our comments and feedback are now up on the Learning Online platform. Use this feedback when you work on your deliverable 2. Next, the outline for deliverable 2 is now available in the updated competition guide. As usual, you can download the new version of the guide from the website. Also, the technical resource group is now accessible to you. You can see their profiles on their email IDs on the online learning platform. You can also read more about them on our website, where you can filter the list by their expertise areas. And lastly, now for a surprise, we have a short quiz for you based on the first 5 learning modules. The first, second, and third place winners will receive gift cards. The quiz will be available from the 10th to the 12th of November. So brush up on your learning and make the best learners win. Now today's webinar is being conducted by Peter Rumsey. Peter is talking to us from the West Coast of the United States. So it's early morning for him right now. Good morning to you, Peter. Peter is the founder. Yep. So Peter is the founder and CEO of Point Energy Innovations, a new consulting firm focused on working directly with owners and developers in the US and globally on the next generation of profitable, low energy, high performance and decarbonized buildings and industrial facilities. He has received numerous awards, including Renewable Energy Innovator of the Year, and ASHRAE's prestigious Award of Engineering Excellence, an award only given 4 other times in ASHRAE's 100-year history. Peter is a graduate of UC Berkeley and a fellow with ASHRAE and the Association of Energy Engineers. For over a decade, he has taught at the Stanford University. We also have with us today Samit Bhaumik as a panelist. Samit is the director of Vera Tattva Engineering Consultants. He specializes in doing high-performance building design at no added cost. Samit and Peter have worked together closely on Infosys buildings. Samit is here to field any specific questions related to costs or practices in India. Now today, Peter will discuss the approach and impact of right-sizing and the interrelationships between different building systems and their impact on sizing for each other. As always, you are free to send in your questions at any time during the session. We will take as many questions as time allows during the session. And with that, Peter, let's get started.
Well, thank you so much, Yashima. I'm very excited to be with you today and share some of my experiences. And as Yashima mentioned, I work and live in the U.S., but I've also spent a lot of time working in India, especially with Infosys, who's one of the sponsors for the Solar Decathlon. So yeah, let's just jump right in here. I want to start by talking about what is a load calculator. You've already been presented or had a module on, how to do load calculation. So if you haven't gone through that yet, I'd urge you to do that. Load calculations are calculations. So a lot of times architects, I know many of you are architects, just say, well, let the engineer do that. But the basics of how load calculations work are actually quite simple. And I would urge you to try to understand how load calculations work, because the load calculations very much impact architecture. And the more the engineers understand architecture and architects understand engineering, the better off we're going to be on buildings, especially when it comes to have low energy buildings. So, what is a load calculation? The calculation that we're talking about is figuring out how much cooling we're going to need in a building, how much electrical service we're going to need, how big is the fan system, how big is the chiller or the cooling unit, and all of these things figure into how much will the building cost, which is ultimately a very important thing. And as a professional working in building design, I will tell you that all of our great design ideas can get undermined if they're too expensive. So we have to be very focused on what we're doing and how much that's gonna cost, and creative solutions. And I think many of you, as you start looking at this low energy, high performance building, design, needs to be something you're thinking about. So Summit is here today also to help give you guidance around and throughout the solar decathlon around how much things cost and what you're doing and how that would fit into the context in India. Okay, so when I look at a space like this, and I talk mostly about office buildings because that's where I do most of my work, but many of these concepts are exactly the same in a apartment building and even a single family home. So anyway, when I look at a space like this, obviously I see people working, but as an engineer, I see, oh, there's all these different sources of heat that are coming into this space that I'm going to need to provide cooling, right? So there's heat coming in. Some of it's going to come through the windows, but some of it's going to come from other sources. It's going to turn into heat. I have to turn on the cooling system to be able to overcome that heat and keep the space comfortable, right? So that's a cooling load. And that's we spend a lot of time thinking about cooling loads. It's one of the first things that we think about. When you have a cooling load, then you will have a cooling system, and then that affects the electrical system, and then you have electrical load that also translates into DG, diesel generator load, backup systems. So all these things are connected. So anyway, I want to start by asking you a question. And there's going to be a poll. And the question is, when you look at this space, what are the sources of heat that are there that we need to provide cooling to overcome? So there's a poll here. And Yashima, I don't know if you want to jump in and explain how to participate.
Sure. So there's a link that I have just shared in the chat window, and everybody please click on the link and type in answers, and we'll take around 30 to 40 seconds here for everyone to put in their response, and then we'll look at the results. So the link is in the chat window.
Yeah. So let's spend maybe 2 minutes on this. Open the link, and you don't have to type in everything. Type in one thing that comes to mind. If you want to type in a couple others, that's also fine. But at least type in one thing.
Yep. So I have just shared the link in the chat window, and So we have varied responses coming in. I'll probably wait for another 30 to 40 seconds. And Peter, then we can share the results.
Great.
Yeah.
And there is no wrong answer. So, and there's no grades or anything. So it's okay to just, if you're not sure, just put in something, you know, that you think, and then we can talk about it.
Absolutely.
Yeah. Oh. Okay, so.
Yep. I think we'll. And
Maybe make it a little bit bigger, and then I'll.
yes.
Yeah.
That's fine.
Okay.
I think we can make it a little more big because.
That's okay. Okay, right. So here we go. And for some of you, the words are going to be a little bit small, but I can read some of them off. So the biggest one is computers, and that's correct. Computers put off heat that goes into the space, and then that's what we need to provide cooling for. People, humans, exactly. People put off heat. Each person is putting off as much heat as a couple light bulbs. Old style light bulbs, not LED light bulbs. It'd be about 10 LED light bulbs. So equipment, computer systems, lighting, correct. Lighting puts off heat. Sunlight, okay, and glazing, yes. Solar heat gain. Sun comes, hits the window, comes through the window, and that's heat in the space. So there's a solar load. And then let's see what else we see. Radiation. Oh, here's one, fresh air. Very good. When you bring in fresh air on a warm day, when it's hot outside or hotter outside than it is inside, which is most days, you have to cool that air, and you have to bring in fresh air into the building to keep it healthy, right? So that's good. There's one other thing that, you know, there's not only the solar load, there's glazing is maybe the right way. There's also heat transfer through the glass. And that is, if it's warm outside and cooler inside, then there's just conduction through the glass. There's also conduction through the wall that doesn't have the glass. There's also appliances, electrical appliances. That's another, if you have anything like a microwave or a fan, all these things put off heat. So this is very good. I think that you, this is a very good word cloud. I think you guys understand a lot of what's going on here. So, you know, so next time you walk into a space like this, you can remember this image. This is how I see the space. People, you know, computers, windows, all those things. That's what I start thinking about. It's, you know, it's just like an architect. When you walk into a space, you start looking at, you know, how did they lay it out? What is it? Is it a beautiful space? Well, I walk into a space and say, well, you know, where are the cooling loads? So, yeah, very good. One thing I want to impress upon you is that for every watt of electricity that we put into lights or computers or appliances, all these things, that all of that electricity turns into heat in the space. For a moment, that electricity turns into light, or it does some useful work on a computer, but ultimately that turns into heat. The light hits a surface, that light turns into heat. Same thing after the computer chip does the work, it dissipates that energy through heat. So all of the electricity that we're putting into a space turns into heat, 100% of it. So one of the things that we do to lower cooling loads is we have more energy efficient lighting, or we'll have more energy efficient computers. So it not only lowers the electricity consumption, but it also lowers the cooling load, right? So on the windows, there's the solar load, and that is sun coming in, the conduction that I was talking about, just heat moving through. It can move through a wall or through a window, and then infiltration. If it's a window system, and that was mentioned in the word cloud there, if there's cracks in the window between the glass and the window frame, or where the window frame is connected to the building, where there's little cracks, infiltration can happen, and that's, you know, untreated air comes into the space. And generally speaking, in commercial buildings, we're trying to minimize infiltration because we're trying to control the temperature and the humidity. We'd rather have the fresh air come in through an air handler as opposed to a you know, crack in the building. Now, there are buildings where, especially residential or single family home, where we have operable windows, and in some climates or some times of the year, depending on where you are, it might be nice to have operable, especially in the evening when it gets a little cooler and you can get the airflow through the house and you can start feeling comfortable just with natural ventilation. So that's a case where, you know, infiltration doesn't matter. But generally in commercial buildings, we try to keep it relatively tight. So digging in a little bit, you know, what is a load calculation? This is a sample engineering load calculation to try to determine the cooling load. And this can be done in a spreadsheet, or it can be done in a software program. You know, in my office, we actually created our own spreadsheet. It's not that complicated, especially for the engineers out there. But for the architects or non-engineers, this can look a little complicated, but if we had half an hour to just go through this one slide, which we don't today, I can explain the concepts here. There's a lot of repetition, but it's multiplying and adding. There's not any really complicated math here. It's just, you know, adding things together. And so it can get fairly involved, but it's not that difficult. You know, we look at what type of glass and how much, type of insulation, what types of lights, and how many watts per square foot, those kind of things. And we add that all together, and we get over here on the bottom right. Can you guys hear me okay? Yashma is...
Yes, you're audible, Peter.
Okay, yeah, there's some electricity instability here. But anyway, yeah, just let me know if for some reason I blank out or I'm dropping out, so I can repeat myself. But
Sure. Yeah.
Okay, thank you. Over here on the bottom right, you see it's total load. That's the thing we're trying to figure out, is how much cooling do we need? And you know, so this is something that's pretty simple. Normally when we're designing buildings, we sit down, architects and engineers, and we go through this. We figure out what type of glass and what type of lighting, and we input all of this, and we come out with a number. And it usually takes a couple of days to do it correctly, but then we can come back and report, okay, the cooling load is this. So it's not that hard of a thing to do, and I recommend that this be done on every building. Unfortunately, there is a different approach that some people use, and that is using the thumb rules. And you might have heard about this, but basically there are shortcuts that you can use that doesn't involve a load calculation. And this is an example of a thumb rule, you know, table, and you can see that it says for office buildings, right? And depending on what percentage of glass, this is the tons of refrigeration, TR, the amount of cooling that you need for 1,000 square feet, or roughly 100 square meters, right? So it's a thumb rule. It just says, just office building, 50% glass, okay, 4.5 tons of refrigeration for every 1,000 square feet. So that anybody could do that. A fifth grader could do that, whatever, a young person could do that. So that's not real engineering, and that's not real design, but people use this when they're in a hurry. So the thumb rules, they have to work for all situations, and including the worst possible situation, right? So a building that's very bad as insulation and lots of internal lighting and all these things going wrong, the thumb rule needs to be inherently conservative so it works in all cases. So oftentimes when I do the actual load calculation, this one, I'll come up with a number that's much smaller for the amount of cooling than the thumb rule. So I think the thumb rules are useful in the very first day of design, just to get a feeling for how much cooling, but real design is where we actually do a calculation, and the calculation's not that hard. There are very, you can get very detailed about the calculation, but calculations typically can be this level of detail, not too difficult. So I would avoid, especially in the solar decathlon, but also as a professional, I would avoid designing around thumb rules. I'd actually use load calculations. Okay. So yeah, you're working on the solar decathlon, which wants to be energy. So what are strategies for lowering the loads, right? So the first thing that we think about is reducing the solar heat gain, right? The windows. How can we get less sun coming in the windows? And so it can be, maybe we have less windows. But if you have too few windows, then you need more electric lighting, and it's not a nice space to be in. But there's better windows, like you might have heard about the low E windows. There's external shading devices on the windows. There's a lot of things you can do to make windows still work really well as far as daylight and views, but reducing the solar heat gain. The next thing that we think about for lowering the loads is reducing the conductive heat gain, either through the window, like double glass and single glass, or insulation on the hard part of the wall, the opaque part of the wall, right? And then we start thinking about how do we reduce the infiltration, the cracks in the building. And then we think about the ventilation. How much ventilation do we need to keep the building healthy? We should bring all that ventilation in, but how do we make sure that we don't overdo it with ventilation, and that we do the ventilation correctly? And then last but not least, very importantly, is reducing the internal heat gain. And the internal heat gain are lights and computers and all the other things. There's nothing we can do about people. People have to be in the building, and people put off heat, so that's fine, you know. But we want to think about, are there low energy lighting strategies? Yes. Are there low energy computers and plug load strategies? You know, laptop computers use so much less energy than a desktop computer. And now that we're in this COVID time, people are being asked to be able to work remotely or be mobile. So the use of laptops is accelerating right now, which is good news for low energy plug loads. I put a link here for a green website that gets into the details of all the different strategies in these 4 categories. I'd urge you to look at that, and this presentation will be available to you afterwards. Okay, so changing gears a little bit, I want to talk about an interesting concept for reducing loads, and that is this idea of insulation. As an engineer, when I was in engineering school, we were asked to calculate how much insulation should we put on a pipe, so that if it has hot water in it or cold water, chilled water, you know, for cooling, what's the right amount of insulation? We know that some insulation is good, right? That a pipe is just going to be, you know, losing its heat or losing the cooling. So let's insulate the pipe, but what's the right amount? And so we had this formula of you add more insulation, you use less energy, you waste less energy, and the insulation costs money. And what's the balance point between spending more money on insulation and how much energy you save through lower heat loss or heat gain into the pipe, right? So, and so what it turns out is there's this thing of diminishing returns where the first inch of insulation, of the first few centimeters of insulation works really well. But as we get more and more insulation, those centimeters of insulation don't add very much value. So there's this point at which stop adding insulation. It's not cost effective anymore. And that's about it. That's how we're taught to think about it. But there is a different way. And I want to explain that to you. So if we add extra insulation, and maybe this is a hot water system in an apartment building, and we combine that with the low flow shower head, which means we use less hot water. We put those two things together, better insulation, less hot water use. What happens is the size of our hot water heating system will suddenly go from, you know, one size down to the next lower size. And so that we can buy a smaller heating system. And hopefully we're doing an electric heat pump heating system, not a gas heating system, right? That's electric is the best way to make a low energy and decarbonized building when it's powered by solar energy, right? So I'm sure you've heard about that and are designing that into your thing, but those heat pumps are expensive. So we want to make sure the right amount of insulation and the low flow shower head. And what we'll find is that more insulation in this case is better or good than the other case where we're just looking at the heat loss through the pipe. The downsizing of the equipment makes it possible to pay for more insulation. And overall, we could end up with a system that's cheaper to build than just the pipe with the insulation and no changes to the size of the heating system, right? So when we look at it as a whole system, this is where we get the cost-effective solutions. And so this is where load calculations and loads come together with architecture. The type of glass, the amount of insulation, those are architectural decisions, not engineering decisions, typically, but they impact the loads and the size of the cooling system, right? So this is where architect engineers need to work together. You guys are on teams together so that you can, the engineer can say, can you please put a little bit more insulation in the wall so that my cooling system goes down one size? And then that going down in size of the cooling system helps to pay for the insulation, right? So this is a key and very fundamental, important idea about load calculations. So I want to talk a little bit about this idea of right sizing and give you some stories and examples from my career. I started out working on a building in Texas, and Austin, Texas in the summer months is similar to, you know, Hyderabad. It gets quite hot and humid. And so we were designing a new building and we did our load calculation. And we were coming up with a number 600 or 700 square feet per ton of operation. So the higher number means smaller cooling. So, but the thumb rule said 400. And we're like, no, we can do 600. And the local engineer said, no, you have to use the thumb rule, 400. And he said, okay, wait, let's measure some other buildings. And luckily there were some very good measurements available for some other state office buildings, same building type, same function. And those measurements were showing 700 square feet per ton, 700 square feet per ton. We even had one that was 800 square feet per ton. And so that was half as much cooling as what the thumb rule was recommending. And so we won that battle. We put in 600 square feet per ton, which is conservative and has safety factor and all these other things, but saved us a lot of money on the construction of the building. You know, smaller chillers, smaller pipes, smaller electrical system, smaller ductwork. Everything was smaller because we right-sized the system. And I want you to remember this for your career as you're a professional, that right sizing is really important. It's very easy to be lazy and oversize everything. It's not my money. You know, the owner will pay for the big system, but no, it's actually, it's going to reflect on not being able to do other things for the building, a bigger building or better finishes and a more beautiful building, because we oversize the equipment, right? So right sizing is a really key with a safety factor, right? But not too much. I also worked on the Asian Development Bank in Manila, Philippines. And this is at the time that I was helping on this building, we were looking at saving energy. It was a 5-year-old building. It was relatively new, but it was using a lot of energy. And there was one thing that was so fun and amazing, is that the transformers for the building were 45 megawatts. This is a 1,000,000 square feet building, right? And so they have electrical system that was 45 megawatts. Now in Manila at the time, they had power outages almost every day. And so they had a generator system, DG system, that was 7 megawatts. And when the power would go off, they would only use 4 on the peak day. It's usually 3, sometimes 4 generators, meaning that the energy consumption of the building was 4 megawatts. And they had 45 megawatts of transformer capacity, electrical. So the electrical system was oversized by a factor of 10. So if they had, you know, with the electrical transformers, 45 megawatts, if they had bought 45 megawatts of DG system, it would have been so massively oversized and so expensive to build, right? So this is how waste happens, is that engineers can be lazy and not really look at what's the right size. So that was very interesting. I've worked with a wide variety of Indian companies, and this is a building in Bangalore where you know, the company is trying very hard to do low energy buildings. So what they do, and these are office buildings for, you know, tech employees, you know, they think about the glazing. See how the glazing is recessed in? So you still have the glass, but when it's recessed in, the direct sun doesn't hit it. But you can also see the light shelf, these vertical lines, horizontal lines, I'm sorry, that has a little shelf that bounces the daylight into the space. So they get the natural light without all the glare and the brightness that makes people's eyes squint, and then they have to pull the shades, and then lights have to turn up, right? So they have better facade. They also combine that with low energy lighting inside the building, low energy computers, laptops mostly, and then low energy fan systems. So they put all this together and it results in smaller chillers, right? Smaller cooling system, half the size of what would be just a standard office building in India. Their generators are smaller and the electrical equipment is smaller. All these smaller things pay for, you know, better lights and pay for better glass and pay for the light shelf. So overall, this building can be the same or slightly cheaper than a standard building. Very interesting, right? So, you know, for this building, the thumb rule would say 400 square feet per ton, the actual 800 square feet per ton. That means half as much cooling. And the electrical thumb rule is 0.8 kVA per 100 square feet. And their actual was 0.4. So half as much electrical. That's the, you know, this is, you know, phenomenally important in getting the price of the building to be more affordable, right? And a high performance, low energy building. So there is this problem though. There's 2 American companies that are working in India. They're global companies now, JLL and CBRE. You might have heard of them. They're real estate companies, and they help big companies find space in office buildings that they're going to lease the space, rent the space. So they have a requirement for cooling load of the 400 square feet per ton in this 0.8 kVA per 100 square foot, right? But a low energy building, it can be so much lower than that. And so we were working with a developer in India, Bangalore, and we said, you know, you should do the better glass. You know, if we do the better glass, the better, you know, light shelf, the better lighting, all these things will result in a smaller cooling system, smaller electrical system, smaller DG. And so they said, the developer said, no, Peter, we can't do that. Because if we do that, then JLL and CBRE will say that our systems are not big enough. JLL and CBRE say you have to have at least this big system. And so every time it's big, so there's no incentive for the developer to make better glass because this requirement is there. Now, this requirement won't last forever, and we've started to discuss this problem with JLL and CBRE, and they will come around. So don't worry about this, but it is one of those barriers, irrational barrier that gets set up, and sometimes we have to work to overcome that. Okay, so let's take another poll here, and I'm sorry, Yashima, do you want to?
Yeah, sure. Yeah, so we'll take another poll at this moment, and I'm launching the poll. So the question here is, what is the estimate of your HVAC system for your solar Decathlon India project? And we have 5 options here: less than 200 square feet, between 200 to 400, 400 to 600, 600 to 800, or more than 100 square feet per ton. So we'll wait for the participants to respond here for another 30 seconds. And
yeah, it's okay to guess. If you don't know and don't have any idea whatsoever, it's okay to not vote. We should have maybe added one in there for I don't know, but it's fine. But hopefully many of you know kind of where you are right now. And obviously it depends on the building type, and it depends on your location, which part of India, you know.
absolutely, yep.
And again, we're not recording the answers, so don't worry about, you know, where you are. It's fine.
Right. I think let's end the poll here, and I am going to share the results now. So
Okay,
here are the
great.
results, Peter. Yeah.
Great. Okay. So here's an interesting distribution. So everywhere from less than 200 to more than 800. So the higher number means smaller cooling system, right? So 800 square feet per ton means there's more square feet for every ton of refrigeration. So generally what you want to be doing in your project, and again, it depends on your location and the building type, you want to be trying to move towards the higher numbers. And it'd be interesting for your building type, what's the thumb rule for India? You want to be trying to beat that thumb rule by maybe double. That would be my recommendation, is try to figure out how can I beat that thumb rule. And you'll need to do the load calculation. So get one of the engineers on your team to sit down and make that spreadsheet and run through. And then the engineer can give you some guidance like, hey, the lighting is our #1 load right now, or the glass is a very big part of the load. Let's work on shading the glass or using better glass or less glass, you know. So that's very interesting. Thank you very much for sharing that. I'm going to close the poll now. Okay. Just a couple more stories that I wanted to share with you. One of them is plug loads really matter, especially in office buildings. And I've worked for a lot of tech companies, you know, in India and in the US and other countries as well. And the plug loads are really important. And so, you know, generally I've measured many buildings, and I find the plug load for computers to be generally about 1 watt per square foot, right? Or 10 watts per square meter, roughly. Sometimes it's a little bit higher, but so often we are demanded to, you know, design for 2 or 3 or 4 watts per square foot. And I remember once when I was designing a building. This other engineer called, it was for a tech company in Silicon Valley. And he called, he was yelling at me on the phone, like this picture, Peter, you're crazy. You have to design for a minimum of 3, but probably 5 watts per square foot. And I'm like, no, I'm not going to do that, because I measured 5 buildings of the same company, and every single one of those buildings is 1 watt per square foot. And so I'm going to design for 1.5 watts per square foot safety factor, good, but not excessive, massive safety factor of 3 or 4 or 5 watts when I'm measuring 1 watt. So people get very adamant and upset about this issue, but in an office building, it's the #1 thing that can make the loads get really high, and you end up with a lot of cooling equipment. Okay. So another thing that's really important is when you're doing a load calculation, what are your assumptions? And this is where architects can be very instrumental. What kind of insulation, what kind of glass, all those things are important inputs into a load calculation. So this is a table that we used on one of our projects in my office and feel free to copy this, of all the inputs that we were using for our load calculation. And then we talk about those with the owners and the architects, obviously the ones on the left more about things like, insulation and stuff, right? And we talk to the team and make sure everybody's on board. And we'll make a recommendation, put some more insulation in there, and the architects will make sure that it gets reflected in the wall section. Okay. So just wanted to end with some of the tips and tricks in load calculations. The first is that your assumptions for the plug loads are very important, especially commercial buildings, office buildings, things like that. Not as much in residential multifamily, but in multifamily, the assumptions for hot water use is very big. We're seeing some multifamily buildings where hot water use, for showers and dishes and things like that, that is the #1 energy user, depending on the climate and other things. So hot water use is really a big deal. Thermal bridging and concrete wall conduction is often wrong and not taken into account properly. So the engineers in the group, you should look at the ASHRAE heat transfer and thermal bridging from if there's metal studs in the wall or different things like that. They should be carefully assessed to come up with the overall insulation value of your wall. Thermal mass matters. So we do have a lot of buildings in India that are made with concrete. They're concrete structural systems. There's a lot of concrete in the building, meaning that there's a flywheel effect in the building. And so as the day warms up and people come into the building, sun is shining into the building, that thermal mass will absorb some of the heat. And so the cooling load is a little bit lower because of that. And sometimes it can be a 25% factor. So in a load calculation, there are simple ways to take advantage or take into account the thermal mass. Document and verify the inputs into the model. I showed you that table. It's really important that you document and you share with everybody, this is what are the inputs. So often people, they don't document that. They don't put it into a table. It's just some input that people lose track of. And then the last thing that I wanted to share with you, when you're using a software tool for load calculation, the experience of the person running that software often matters more than the accuracy of the inputs. So some of the software tools that are out there are very tricky to use. So that's why I like using a spreadsheet that we can build up. It's not as complicated as the software, which can have very sort of subtle tricks and tips in and of itself. If you use the software, just use it carefully and spend the time to learn that software. So with that, I'm going to end my presentation. I very much welcome your questions and the discussion. I'll start by answering the questions where appropriate or where Summit has some information to add. He'll also chime in. So go ahead and put your questions in the Q&A box, and Yashima is going to sort through them and read them out. Thank you very much.
Thank you, Peter. We have a few questions coming in during the presentation, so we'll start taking them up now. So Great. The first question is, So the first, a compliment, a wonderful presentation, and appreciate the session with Solar Decathlon India. And if you may suggest a good book or reference to learn the fundamentals of heat transfer in buildings.
Yeah, you know, it depends on how fundamental you want it to be, but you know, normally I'd say ASHRAE handbook fundamentals is where it has all the here's to and principles of HVAC from ASHRAE that's also available that that talks about how you do load calculations. It's the cookbook. But I would also say today online, there's very good information online. There's everything from YouTube videos about load calculations, Wikipedia articles, and other how-to websites. So ASHRAE is the go-to to get, you know, the textbooks and the data and all that, but like the higher level, getting introduced to the concepts, you know, I actually think that Wikipedia are good resources to get started. But definitely as you get into it, ASHRAE is the best place. And they have a textbook, in essence, a teaching book called The Principles of HVAC. And then they have the reference book, which is called the handbook. And the one you want to look at for load calculations is called the fundamentals.
Right. Also, just to add, learning module, we have provided additional resources. So, you know, you can take a look at that, and yeah, you could refer them as well.
In fact, one of the books which is listed in the additional resources is a book by Anant Narayan. It's a very good book. You know, it's a book written by a practitioner. It's a very, you know, I strongly recommend everyone to please read the book. It's very easy English. It's written up by someone who's spent a lot of time in the industry. So it's a very nice practical book to read.
Right. Thank you.
What type of book?
It's a book by Anant Narayan. It's Fundamentals of Air Conditioning Refrigeration. It's a very, very nice book. You know, good read.
Great.
Great. Yeah. Okay. Next question. Why do we need to do the load calculations for a particular time in a day rather than for the whole day?
Yeah. So the concept is theoretically, there's 1 hour of the whole year where the maximum cooling is occurring. And that 1 hour of the year is when everybody's in the building, the temperature outside is maximum, and the sun angle is exactly right to get maximum sun into the window. So there is this question of what day of the year is that occurring, and what time of day? Is it that, you know, as the sun at noon it's high and then it starts coming down? Sometimes the maximum cooling load is when the sun is coming down, so at 3 p.m. or 4 p.m. and the sun is coming in the window. So you know, when we're doing a load calculation, we'll test 2 or 3 times during the day and use a temperature that's relatively appropriate for that time of day. The software packages, they'll test every hour of the year and find where the maximum is. And sometimes in our spreadsheets, we'll actually get the weather data and we'll put in all the days of the year every hour. And then we'll also, you can do it in a spreadsheet, find the maximum. It's a little bit more complicated. But you know, the simple load calculation is you choose a day when it's a sunny day, it's a maximum air temperature, and that is a given. And you choose a sun angle that's not maybe the highest point of the day, a little bit in the afternoon. And that usually gives you the maximum.
Maybe I'd like to add here, you know, there's a spreadsheet along with the self-learning model also, but the spreadsheet lists out all directions of orientation, right? So, but you don't have the sun on all sides at the same time. You just have it on peaking on one side at any point of time. So you need to, you know, so there is one point of time when the cooling load actually peaks for that particular building, and therefore you need to estimate for that particular hour so that your equipment is not undersized.
Correct. Yeah.
Right. Moving ahead, next question. What are the cooling system differences that come across when considering humidity levels in the area? Whether the air outside is drier or more humid, that would cause discomfort.
Yeah. So one of the more subtle parts of a load calculation is that humidity question. And so this is very much on the engineer's side. But when it's humid, we not only have to cool the air down, we also need to dehumidify the air. And that is a load that takes cooling energy to dehumidify air. And the way that we normally dehumidify air is through cooling the air down, usually to somewhere in the neighborhood of 13 degrees Celsius. And then that all the water condenses out, and then we bring it into the space, and it results, typically if we have a space temperature of 23 or 24 degrees C, then it's about 50% relative humidity. So that's how we dehumidify. It's a very important load. It's one that the engineer has to take responsibility for. So, and that's why I was saying ventilation is a load. So ventilation is the air that we bring in. So that's where we cover the humidity question. When it's a dry day, it uses less energy to cool the air because we're not dehumidifying it. So it might be that in Hyderabad, which has dry, hot days and also hot, humid days, it could be that the maximum cooling load is when it's let's say 32 degrees Celsius and humid, but the highest temperature of the year might be 35 or 40, right? So, but it's dry that 35 or 40 degree day. So the maximum load on ventilation is not always when it's the maximum temperature. Again, that data is published, ASHRAE, they have for each city in India a peak condition for high dry days and also high hot humid days. And you can look at those and understand, which one, or do the calculation quickly and which one's the maximum.
Maybe if I can add here, the ambient humidity is an important factor, because if you're in a space which is coastal area and you have a lot of humidity around you, it automatically excludes a certain kind of system. For example, you can't use an evaporative cooling system if it is already very humid outside. So it's essential to understand. The question was whether humidity is important in deciding the system. Yes, it is extremely important, because that can exclude some systems, which would otherwise be, probably considered in some other place.
Correct. Yeah.
Right. Thank you. Let's take the next question. In your opinion and experience, you feel that HVAC load in India is resulting in large building operation costs. So, what's your opinion on using trees strategically to reduce heating loads?
Yeah. Trees are very important in many ways. Sorry, hold on. They can be used to lower the cooling load as long as it's not a high rating, right? So there's a couple things about trees. One is that ASHRAE asks us as engineers to not take into account trees, because what if the tree dies, right? Is the ASHRAE thing, and then the tree gets cut down, and so that's a conservatism. But if you have a building that has on the south side a whole row of trees, well, one might die, but the other ones are still there. So, but trees actually help not only in shading the building and lowering the solar load, but if you have a tree-lined street, it also blocks the sun from hitting the street, which usually is a dark color, absorbs a lot of heat, and creates what's called this urban heat island effect. And so the air temperature where there's no trees can be high, and lots of cars can be 5, sometimes even 10 degrees Celsius warmer than where there's trees and less cars. So you'll see in the middle of a city, it will be much warmer than out just say 10 or 15 miles away where the city is less dense and there's more trees. So highly recommend trees. if it's possible. They can create shade on the building, but they can also lower the air temperature around the building. And they're, they're beautiful. And as human beings, we respond. There's lots of studies now talking about biophilia, that we respond positively on a subconscious level even to nature. And so there's an air quality benefit. There creates habitat. Trees have so many benefits, and yes, they can lower cooling loads.
Right. Thank you. Let's take the next question. So, how different is a radiant cooling system from a conventional system? How different are the thumb rules?
Yeah. So as far as the thumb rules go, there's a amount of cooling that we need to provide, and that, you know, is based on, you know, the windows, the lights, the people, computers. That's independent of the type of system. So we could have an air-based system or a radiant system, but the load is the same, and so our square foot per ton of refrigeration should be roughly the same. Now, the difference with radiant, there are some, you know, differences. One is that we don't have the fan energy. Fans make heat. All the fan energy in watts turns into heat. That is another load. And so this is one of the reasons why I like the radiant system. I very much like radiant. We've done lots of radiant systems in India. It's because we don't have the fan energy, which is lower energy, and we don't have the fan heat. So we have less cooling load. The radiant system embedded into a concrete structure also has a little bit of a flywheel effect, and so we get this thermal mass. We start to activate and work more closely with the thermal mass of the building, and that does also help to reduce the peak loads. It's a little bit more of a subtle thing, but you know, it's maybe a 5 or 10% effect of reducing the cooling load because the thermal mass is more part of the system. But it's a little bit of a subtle thing. There's lots of information written up in ASHRAE and other places. This is a detailed version of the information about radiant systems and how to design them as far as the load calculation goes. But radiant systems are one of the lowest forms of cooling available. And the solar decathlon projects in the US, like when I went to the last one that I went to, half of the projects actually used radiant cooling and heating. Yeah.
Right. Thank you. Next question. Can you suggest a few key points to keep in mind while doing heating load calculations, keeping in mind the pandemic?
Yeah. So I think the number one thing about the pandemic is that general, one of the recommendations, there's two recommendations. There's lots of recommendations, but two that affect the HVAC system. One is we should bring in more fresh air. And so, you know, there's only so much that we can bring in before it gets out of hand or somewhat ridiculous as far as the cooling loads are concerned. So it might be that we need to design systems that, you know, our normal ventilation rate is X, but with the pandemic, for temporary periods of time, you know, a year or something, we bring in 2X amount of ventilation. So if that's the case, then we're need more cooling or heating. If you're in, you know, a climate that needs heating, northern India and such, then, you know, we need bigger systems for more ventilation. That would be one thing. But somewhat offsetting that is that one of the recommendations is that we should, you know, have a little bit more spacing between people, the social distancing. So there'll be less people in office buildings. So that helps to lower the load, cooling load. The more ventilation would raise it. The most important thing is that we have very good filtration. What our recommendation is that you use MERV 13 to MERV 15 filters. This is the rating of the cleanliness of the filter. And that will be able to filter out these small aerosolized particles, which can be the transmitters. So I think the best things you can do, social distance in an office building, social distance, wear a mask, and you have very good filtration. And bringing in more air will help, but it's not going to fix the problem. Much more effective are this filtration mask and distance. Yeah.
Right. Thank you, Peter. Next question. Can you share some of your experience in designing the NREL research support facility in Golden, USA?
Yeah. So just to be clear, I worked on the integrated system laboratory, the ISEF or something, ISIF. And that is a very interesting building where we have a supercomputer and laboratories and offices all in one building. We use the waste heat from the supercomputer to heat the office building and a laboratory. Very cool. The RSF project, I do know about it, but I wasn't the designer. So I just want to make, not take credit for that building. It's a great building. That's an office building. It's a net zero energy office building. And what they did in that building is they followed exactly what I was talking about earlier in the presentation, where they lowered the solar load. They had very good windows, shading devices. They even have this special device that makes the daylight go deep into the space. You can look, there's videos and lots of good information online about it, but this light reflecting light shelf system. So they had, good windows, good solar control, good insulation, very good lighting, low energy computers, and they had also a narrow building so that the daylight could fill the space with natural light, not too much of it, and the lights could be turned off. So they did everything that is right about the fundamentals, but they just did it in a big building. And then they did do one interesting thing, which is in Colorado. It's a unique climate. It's like hot in the day and cold at night. The temperature drops quite a bit. It's a dry climate. And because of that, they get these cold nights, and they have the foundation underneath the building, concrete, a basement space, and they run air through that at night, cool that down. And then during the day, they can run air from the building through this foundation that's been cooled down at night. So it's a form of thermal mass or thermal storage. Very creative. You can do the same thing with just a tank of water if you have that kind of temperature difference from day to night. But it's an interesting building and lots of good concepts on it. None that are too weird other than that one I just described, but they just did all the right things and they did it carefully, and they came up with a low energy building, and then they put solar PVs on the roof and the parking structure next to it, and that was enough for the whole building. It's quite a large building.
Yep. Thank you, Peter. Next question. How can we reach feet per ton cooling?
You broke up. Can you repeat the question?
Yeah. The question is, how do we reach to a value of more than 800 square feet per ton?
Yeah. Yeah, so I think that, as I said, I've worked with the companies in India in achieving 800 square feet per ton. And it's just following all of the fundamentals, like not some of them, but all of them. It's you have a checklist and you do all of the things in the checklist, not just half of them. And so, I think the strategy is, better windows. And, I showed you a building in India, a photograph of like the windows recessed, good shading, everything is done right about the windows. That's how you start it. And the quality of the windows is good. The insulation in the wall is good. And then low energy LED lighting that's dimmable automatically, that responds to the daylight coming into the building. The low energy computers, if it comes in at somewhere between 1/2 of a watt to 1 watt per square foot, that's good, and that would reflect the low energy computers. And then the HVAC system being very energy efficient. So those the lowest energy, the 800 square feet per ton is usually happens when you have radiant system. So it's, just pumping energy is much less than fan energy. They do have fans for ventilation, but it's much less air. But even those fans are efficient. Everything is very efficient. And you put that together and you very easily will get to the 800 square feet per ton.
Just to give the attendees a sense of the numbers in India, typically these could be as bad as 150 square feet per ton or going up to 400 square foot per ton. And the question is, how do you reach a value of greater than 800? You need to go through the solar decathlon modules again. Do all of them right, you'll reach 800 square feet per ton.
Yeah. I mean, the 800 it's possible, it's aspirational, but it's not the easiest one, and that's why a lot of people end up at 400 or 150 or because it's easy to just, forget about it, but if you want to do it, you have to work hard. The winning team on the solar decathlon will be the ones who work a little bit harder to get the numbers higher and do everything on the checklist, not impossible. But yeah, go ahead.
They're not going to make it easy for everyone today.
Yeah.
Right. Let's take the next question. So would you recommend to do load calculations for a naturally ventilated building? If so, how does it help?
Yeah. Yes and no. Natural ventilation, if you think about it, like traditional architecture, for India, like 100 years ago, there was no air conditioning and there was no load calculation. And there's so many buildings that were done very nicely. The ones that have persevered are things like temples. And there's so many great examples of naturally ventilated older temples. They use thermal mass. They block the direct sun and things like that, and they had no load calculation. So yes, you can do a naturally ventilated building without load calculations. But now today we have lots of tools at our disposal. One of the things that is very good with natural ventilation is to do a computational fluid dynamics model of how air is going to move through the space. That's really important because you want, in a naturally ventilated building, it's not just about opening a window. You need to get air moving through the building to take the heat away. So I do actually think, excuse me, I do actually think that doing a load calculation can be valuable. And if you have the ability, and this is advanced, to do, like the engineers, to do a CFD, computational fluid dynamics model of air moving through the building, and that will show you how big do the openings need to be, and you can start to optimize the natural ventilation. And so I do think that calculations are valuable in naturally ventilated buildings, and especially, if you're trying to do something that's a little bit of a hybrid of traditional architecture with new architecture, and you're going to have windows and things like that. So yeah, I would recommend doing it, but it's, it has been done for many, many decades and centuries without, so.
Right. Thank you, Peter. Next question. Can you please guide us on hybrid HVAC systems, how to efficiently manage low energy cooling devices and ACs together throughout an year?
Throughout the year?
Yes.
Okay. So, I think that's like I am giving another seminar about HVAC system design and things like that. And so we'd want to get into it in a little bit more detail, but hybrid systems are interesting. There's lots of different types of hybrids where we're combining one system with another. For example, someone mentioned evaporative cooling. So some climates in India, evaporative cooling will work for part of the year. It's very low energy. And then you need compressor-based cooling. And that's when it's, evaporative cooling works when it's dry, hot and dry. And then we need the compressor cooling for when it's humid and hot, right? So we need to get the, water doesn't evaporate as well when it's humid. of course. So there's different types of hybrids. That's one example. And so you need to size, the question is on load calculations, how do you size the things? Well, what I would do is the size the one system for the system that it's being designed for. So in this example, we've got the compressor-based system for dehumidifying. We'd find the most humid day of the year and we'd size the system for that. And then for the evaporative system, we'd look at not the most humid day, but the hot, dry day and size for that. And then it's a question of which one is used on which day. And in this example, it's looking at the humidity. So there's other types of systems, hybrid systems that, one system provides a modest amount of cooling and the other provides like on the high day. And so you decide you want to use the lowest energy one as many hours as humanly possible. And that's fairly easy to figure out because we've got weather data, hourly weather data for every city. And we can say, okay, well, this particular location in this day of the year, it's a cooler day, so we can use the lower energy cooling system. Like natural ventilation hybrid. One hybrid is natural ventilation on cooler days. Places like Delhi have cooler days of the year. And then we'll use the compressor-based cooling on the hotter days of the year. And it's a matter of deciding when you switch over. And you always want to, favor the low energy one as long as humanly possible. And that's, it's a relatively easy thing to figure out in your hourly data.
Right. Next question. How does the indoor design temperature affect the heating and cooling load?
Yeah. It does affect it, but not as much as what you would think. Because, if we say on the heating, we're going to, heat up to maybe 18 or 20 degrees Celsius or something like that. The difference between 20 and 19 or 20 and 18, it's not that big of a difference. The bigger difference is, what kind of glass and insulation and the ventilation. Same thing on the cooling. The difference between designing for 25 or 24 for our cooling set point is not gigantic. But it does matter. It does matter. There is this thinking, like in ASHRAE, there was thinking for a while that it started to change, but that we have to design all the cooling systems for like 22 Celsius. But I've been in lots of buildings in India where like 26 is fine, right? And so the difference between 22 and 26 does actually matter. And it can start to be a 10 or 15% change, or an extreme situation, it could be even 20%. But, my feeling about it, and I think an important thing when you become a professional in this field, is that we want to say that we can do low energy buildings without sacrificing health or comfort. We can still deliver a quality building. If you say, well, we can do a low energy building, but the temperature on the hot day is going to be 30 degrees inside the building, it's not as attractive or interesting to people who are building buildings, the people with the money. They're like, well, I don't really want 30 degrees. I want 26 or 25 or 24. We need to be able to deliver a low energy building that can meet those conditions. And we can. Over and over again, I've been able in my whole career to meet the criteria, but do it in a low energy way. So temperature matters, but it's not everything. And we can deliver, the comfort that's needed. So in your decision making, you should talk about what the temperature should be. And, the wider they are, or the closer they are to the outdoor condition, the less energy you're going to use. So there is a little bit of incentive to go there with, higher temperatures in the heat, in the cooling days, and lower in the heating days, but don't go too far with it, would be my recommendation. No, don't really need to.
Right. Thank you, Peter. Next question. Do we have to take a peak solar radiation hour for calculation of solar radiation on building envelope, like you had shown in the office Excel sheet?
Yeah, so the peak solar radiation might be at 12 noon, on I don't know, sometime in, June, July or something like that. That might be in the weather data, the peak, but the building peak might not be that same day or that 12 noon. It might be 3 p.m. As I was saying, when the sun sort of comes around, it gets lower and it comes into the window. Like we could have a window with an overhang. And if the sun, when it's very high, that overhang blocks all the sun from the window. But it's later in the afternoon when the sun comes in at an angle that the overhang is not as effective. So it's not a given that you take the maximum solar radiation number from the weather file and use that. You need to think about the angle of the sun and such. So a lot of times what we'll do is we'll find like a high radiation day and maybe look what is it at 12 noon, 1, 2, 3, 4, and we'll do a test. We'll do a calculation for 12 noon with our overhangs, and then we'll do a calculation for 3 p.m. and then a calculation for 5 p.m. But remembering that each time it comes lower, it also starts rotating and you don't have as much sun hitting the glass because it's coming from the side, not directly on if it's south-facing glass. So you need to test 2 or 3 sun positions and see which one is giving the maximum, right?
Right.
Yep. I wanted to ask you whether all of these teams are going to be doing energy simulations with their software, and you talked about the fact that there might be issues with user quality input or input quality, etc. But despite that, how would you tell them to use the energy simulations to do rightsizing?
Yeah, I think, a quality energy simulation is a perfectly acceptable way to come up with the peak load. And so in the simulation software, it does give you a cooling load requirement at every hour of the year. And so you can that's a very easy thing. You look at the output and you just find the maximum. Now, what I would suggest is you put a little safety factor on there. I like to use 20% safety factor. That's totally fine. And that's where if you look at and you've done the software calculation correctly, you have a good building, it's very easy with the safety factor to be at that 800 square feet per ton. When you're doing the software, do be very careful with it. I would check it with a person doing it. I'd have another person on my team double check it. Make that table with our input assumptions and make sure they're all correct. Share that with the team. Where you have the ability to have a second pair of eyes, look at that, the energy simulation, do that. And do the work and then come back to it a week later and, do as good of a quality job you can possibly do. And one thing that the thumb rules are useful for is to make sure that, you're somewhat in the same area. Like if the thumb rule says 250 square feet per ton and you came out with like 2,000 square feet per ton, then it's a problem, right? That you maybe made a mistake in the software. And so that's the one area I think thumb rules are good in just sort of boundaries that if we know if we're way too far away from those boundaries or the thumb rule said something went wrong in the calculation or the simulation. But yeah, simulation's good. I like to do simulation and the manual spreadsheet calculation. We oftentimes do both in our practice in our office, just to be double sure. But I think if you're doing the energy simulation, that would be an acceptable way to come up with the loads.
Right. Thank you, Peter. I think we'll take one more question for today. And so Peter and Samit both, I would like you to talk about the kind of safety factor you use in your practice on top of your calculation loads.
Samit, why don't you go first? I'm curious to know. Yeah.
So it really depends on how much information we get from the client and how clear we are about the requirement. But a typical safety factor would be in the range of 15% or so, 10 to 15% or so, the higher side being 20%. But again, I mean, we have to be careful. If you have a lot of, very clear information or very distinct information about the equipment loads and lights and all of those things, usually we don't have all of this information when we're designing the first time. But if we do have them, then you might actually bring that safety factor down to about 10% or so, to 7.5% also, if if you do have good information. So somewhere in the range of 7.5 to about 15% or so, as a rough thumb rule, so to say.
Yeah, that's very interesting. The more we know, the more certainty we have about what the design is, the type of lighting, the type of plug loads, the smaller the safety factor can be. I will say that whatever your safety factor is in India, like 7.5%, I probably am going to double it in America because there's so many damn lawyers here. And we have to be extra careful in the US because if something goes wrong in a building in India, they just fix it, and if something goes wrong in a building in the US, they call a lawyer, right? So engineers in the US tend to be a little bit more conservative, and our safety factors are a little bit higher, and that's why I said earlier 20% is one that I use. But we do see engineers using in the US like 25 to 50%. It's kind of crazy, the safety factors that these guys use. And when they get up to the 50% safety factor, you might as well just use a thumb rule, because at that point it's so oversized, So, but I did want to end with a quick closing comment, Ashma, if that's okay.
Sure. Yeah.
Yeah, I want you guys to know, I hope you're having fun with this. I want you to have fun with this competition. You're going to learn a ton by doing this. Designers of buildings, if you choose this as a career after you graduate, you're learning information today by participating in the Solar Decathlon that is going to have a huge impact on India as a country. And what we need to do as designers is understand that the work that we do, it far outweighs our personal carbon footprint. For me, I've done a calculation, detailed calculation. My professional carbon footprint from designing is 1,000 to 2,000 times more impactful than my personal carbon footprint. And, I do, unfortunately, before COVID, I do fly a lot. I have a high carbon footprint for an individual, but my professional carbon footprint is vastly higher than that. The number of people that design buildings in India is probably in the neighborhood of 1 to 2 million people. In a country of over 1 billion people, that 1 to 2 million people, it's a very small number. That group of people is responsible for somewhere in the neighborhood of 30 to 40% of the carbon footprint of India. And the same thing in America, and the same thing worldwide, is that designers of buildings have one of the most outsized impact, potential impact, good impact on our big #1 challenge over the coming century, your guys' lifetime, and that is reducing carbon footprint. So it's not necessarily appropriate for an American person to tell you guys about reducing carbon footprint. I have a much higher responsibility than any designer of buildings in India, because generally Americans have very high carbon footprint. I get that. But India is in this road to modernizing and becoming a fully modern society that's going to include building so many buildings over the next 50 years. You guys can design buildings that have half the carbon footprint, or ultimately no carbon footprint at all, if you do the right thing. And that is, don't use gas in buildings, make an all electric building. And then we're going to connect every one of those buildings that you guys designed, low energy. We're going to connect that up to renewable energy, solar and wind, storage, and other renewable sources of energy. And we're going to make decarbonized buildings. And you guys are going to look back and go, that was great. And when you're a grandfather, you can tell your kids, I did that. I helped to decarbonize the Indian economy. So I'm very excited that you guys are doing this, and you guys will be the leaders in your field as soon as you graduate. People are going to be asking you how to do this.
Thank you, Peter. That was very motivating. And with that, I think we are done with the session for today. Very informative session. Thank you, Peter and Samit. The Q&A was very helpful too, and I hope that our participants have made the best use of the knowledge and practices that you've shared with us today. Thank you everyone for participating so actively, and we will see you tomorrow at 11 a.m. for the webinar on Design Builder.